every time we talk about measures, the objective is to integrate functions. Now, in the past few videos, we were learning about product measures. We learned that if I give you two measure spaces, we can define a new measure from those two called the product measure. And of course, now the objective is, can we integrate with respect to this measure? In this video, we're going to start with some of the basic definitions that will be helpful for us to define integrating characteristic functions. Before we start, let me remind you that you can support the channel in many different ways. You can donate directly by clicking the Thanks button at the bottom of the video. There are also some t-shirts you can buy from our store, or you can become a member of our YouTube channel. You can do this on Patreon if you want access to some other merchandise, or directly on YouTube. By becoming a member, you get access to some of the exclusive videos we post on YouTube, and you also get access to the boards that we make on each video. If you want to become a member, you can do so by clicking the Patreon link in the description or by going to our YouTube channel and becoming a member there directly. Let's get on with the video. So in the past few videos, we learned that if I gave you, let's say, two measure spaces, x with a sigma algebra, mx and the measure mu, and another one, let's call it y with a sigma algebra, my, and the measure nu, then from this we learned how to define this product measure that we denoted as mu times nu. Now this is a measure in the product space x times y with the product sigma algebra, which is mx product with a circle my. So if you don't remember these definitions, I do recommend you go back and check out the previous videos. Now, as I said in the introduction, our objective is to integrate now with respect to this measure. What do I mean by this? Well, if I define some function, let's say f, from our product space to the real numbers, then what we want to do is try to calculate this integral of f, but now, because f is defined in a product space, this integral will be an integral of two variables with respect to the product measure. Now, we have no idea how to do this unless we know more information about this product measure. We have defined integration with respect to one measure, but usually that is when we know exactly how that measure behaves. But now, all we know about the product measure mu times nu is only known via mu and nu as separate measures. So ideally, what we want is to try and see if we can, instead of integrating this, maybe this can be equal, we don't know, but hopefully we can somehow integrate first with respect to one variable, let's say with respect to mu, and then, now this will be a function of y, then we will integrate with respect to nu. Now, we don't know if this is true, it won't actually always hold, but this is the kind of things that we're now looking for, because we don't really know much about this measure, the product one, but we do know things about each measure individually. And likewise, we can do the same thing or hope for the same thing to hold, but now integrating in the reverse order. Let's say now we first integrate f with respect to nu, and now this will be a function of x, so we will integrate this with respect to nu. So we're not going to quite get to this on these first few videos, because first we need to define how to integrate on characteristic functions, which is what we always do. And for that, let's start with some intuition. So from primary school or kindergarten, if I gave you some rectangle with points like this, and I asked you how many points we have, probably you almost never counted each point individually. What you most likely would have done is say, well, I have 3 points here, and I have 4 points here, so the total number of points is just 3 times 4. Now, the reason why we say this is, well, if I fix this point here and I just look here, I have 4. Then for this one, I have another 4. For this one, I have another 4. So I have 3 times 4 points, which is this. But you could have also said, well, now for each point here, I have 3. So here, another 3, and so on. So actually, I have 4 times 3 points. Now, of course, these two things are the same, but there's just two different ways of looking at the same thing, calculating how many points we have in a rectangle. Now, let's move from kindergarten and maybe go into primary school. Now, instead of a lattice with discrete points, we are giving a rectangle. Let's say that this rectangle has side lengths L1 and L2. Now the area of this rectangle, you would have said it's L1 times L2. And this again follows from the same sort of intuition, but now brought up to some infinitesimal level, where we're saying, well, for each one here, I have L2 mass here, and I can do this L1 times. So in total, I have this L1 times L2. And likewise, for each point in the L2 side, we have L1 mass here, here, and so on. Of course, this is not very rigorous, but this also brings us to the area formula L2 times L1. Now, I'm only saying trivialities here, but this is all based on how we are measuring sizes. And if measure theory is about anything, it's about sizes. So measure theory is all about how we generalize this notion of a size. And what we're doing here to measure the sizes of these shapes is we're taking these things that are, let's say, slices. So we're slicing a figure in horizontal and vertical pieces. So now maybe we want to do something similar to this, but with respect to our measures. So this is what we are calling X and Y sections. So let's go back to the beginning. Now I give you two measure spaces, X, sigma algebra, and a measure, Y, sigma algebra, and a measure. And let's take some set in the product space, X times Y. Let's say that this is our product space. Then our set E can be something like this. Well, we're going to define the X section and Y section of E, and we're going to denote them with E sub X and E sub Y, respectively. So what's EX? Well, I'm fixing some element X in the space X, so here in the domain. And I'm going to look at all the elements in Y such that the point XY is in E. So I look at this element Y, and I say, oh, is XY in E? Yes, it is. So Y is in this set. Now, what about this point? Well, XY is that, and it's also in E. So basically, we are getting this slice. If I change my number X, then I will get another slice, and so on. These are the X sections of E. Now, of course, this is a subset of my space Y because it's giving me all this range of numbers. And likewise, the Y section, E super Y, is now going to be, well, all the elements X in X, such that the same happens. XY is an element in E. And now this is, of course, a subset of X. So now we fix an element Y and we look at all the elements in X. So all this range of elements in X are those for which XY is here in E. If I change my value of Y, then of course get a different Y section. Okay, so this is again just generalizing this very trivial thing that we know how to do since kindergarten to a more general setting, which is the setting of measure theory. Let me give you one more definition, which again is not too complicated. Now we're going to see the X and Y sections of functions. So if I give you a function f from space, the product space, to the real numbers, then the x section, fx of f, is going to be a function from y to the real numbers. And these definitions are a bit funny. So fx of y is f of xy. Now this seems a bit strange. Let me define the y section and then we can see why they are defined this way. So fy, y section of f, is now going to be a function from x to the real numbers. And it's defined on a point x, again, as f of x, y. So what is this? Well, let's think about this. So this is my space, my product space, say x, y, and my function goes from this domain to the real number. So it's going to be some kind of surface. Of course, this is all just abstract thinking. So f is going to be some kind of surface like this. And now the thing is, okay, I fix some point x. To look at the x section, I fix a point x in my space x. And I will look at the function that looks at only the values of y for this fixed value of x. What am I saying? Well, let's come up here to where my function is. And now I think about all the values of my function that are basically here. For each value of y, I look at these different points. So I'm going to have something like this. This is going to be my fx for this specific value of x. If I take some other value, my function is a bit poorly drawn, so this is quite difficult. But if I take another value of x, then of course now the x section is going to be a bit different. But we're basically doing the same. We're kind of slicing now our function into these vertical strips. And now the same with fy. So now we fix a value y. We look at here and we say, oh, well, now I want to take all these values f of xy here. So that's going to be something like this. And again, for another value y, it's going to be, well, all these values that have this domain. So it's going to be something like this. So now for functions, my sections, my x and y sections, are now new functions that go from the other space to the real numbers. Okay, so far these are only definitions. We don't really see how they relate to everything other than from this very basic intuition that we have from primary school. But we're basically doing the same thing. So now let me finish with a very short lemma. This lemma is actually quite simple. I'm not even going to prove it. Um, Basically says that if I take some set E, now this is not in the product sigma algebra. Here what I'm saying is E can be decomposed as a product of two elements in the sigma algebras of x and y respectively. And this is the notation is different from the sigma algebra notation. So I take some set like that and I take the x section. Remember we said the x section was a subset of y, and so it makes sense that it's now in the sigma algebra of y. And this will happen for all the elements x in x. Remember, we take a point x, we fix it, and now we look at the section. Now these sections will all be in the sigma algebra of y. And the same now for the y sections. So you fix an element y in y, and this section, which again is a subset of x, is actually an element in the sigma algebra of x. And now a very similar thing for functions. So if I take a function that's measurable with a product sigma algebra, then the x slice is measurable in the y sigma algebra. Remember the domain of this function is y. So this is a function from y to the real numbers. So it makes sense that it's y measurable. And this will happen for all points x. Likewise, the y sections, again, these are functions from x to the real numbers. These are x measurable, or sigma algebra of x measurable for all y. So what we're saying is all these yellow lines, these are the x sections of this function f. Well, these are all functions that are all y measurable. And remember, we like these properties of measurability for functions because it means we can integrate. And the same for the x and y sections now of a set. Of course, we're going to be using this to integrate characteristic functions. So now each of these sets are in the corresponding sigma algebras of y and of x. So with this, we'll stop here, and in the next video, we're going to start with the integration of characteristic functions. And we'll see that we have some complications, and we have to introduce something that's called a monotone class, which causes a lot of confusion, but it's just a technicality that we'll get through in the next video.